Okay, I know there's already been two answers to this problem, but I thought I'd add a little bit different perspective. We're going to use partial fraction decomposition to rewrite this integrand. And in order to do that, the denominator needs to be in factored form. So I factored out an x squared from this denominator right here. And there's a theorem on partial fraction decomposition that says when the factors of the denominator look like this, it can be decomposed into fractions that the sum of fractions that look like this: a over x plus b over x squared. If this was an x cubed, you'd have a plus c over x cubed. So you need one fraction for each possible power on the x. And then this is what we call an irreducible quadratic. You can't actually solve for x, the set of real numbers. So the numerator has to be the form cx plus d over that irreducible quadratic. And then if you picture multiplying through by this denominator right here, you get this numerator. And when I take this denominator times a over x, one factor of x disappears, and I got ax times x squared plus 4, and so on. Now, you can equate coefficients at this point by multiplying all this out. But sometimes there's a little trick you can do to make it work a little bit easier. If you can find a value of x that turns all but one term to 0, you can substitute that value for x and see what happens. So I can see right here that if I put 0 in for x, this term will become 0, this term will come 0, but this one won't. So if I put 0 in for x, the left side becomes 16. The right side becomes 4b. Boom, I get b equals 4 quite easily. And so now I'm going to rewrite that equation, but wherever I see the letter b, I'm going to put in a 4 right there. And there's no other values of x that will turn terms to a value of 0. So we have to equate coefficients. So now we're going to multiply all of this together. Distribute this 4, distribute this x squared, and equate coefficients. So for x cubed, on the left, I've got 7x cubed. On the right, if I search for terms containing x cubed, I got an ax cubed and a cx cubed. So you can picture it like this if you want, but then if you divide every term by x cubed, you get a plus c equals 7. Now if we search for the x squared terms, on the left the coefficient is 7. On the right we've got a 4x squared and a dx squared. So 7 equals 4 plus d, so d equals 3. And finally, if I look for the terms containing the variable x, I've got a 4ax. Oh, that's the only one. That has to equal 20. 4a has to equal 20, so a equals 5. And if a equals 5, I can come back to here and say, if a is 5, c is 2. By the way, I noticed that I have a over the x, the denominator of x, whereas this example problem has a over the x squared. But now this is the fraction decomposition of the original function. These two integrands are equivalent. This 2x plus 3 over x squared plus 4 I can break apart into two fractions. 2x over x squared plus 4. The antiderivative of 5 over x, of course, is 5 ln of x. For this term, we'll raise the exponent by 1, multiply by the reciprocal of the new exponent. So probably negative 4x to the minus 1, or negative 4 over x. Here, substitution, let u equal x squared plus 4. We'll get another ln there. And here we'll probably use the antiderivative of inverse tangent. I'll leave that to you. There you go. Hope that clarified some of the things you can do when you're doing fractional decomposition. Okay? If you have any questions, post a comment.